I'm ready.
Okay, so thank you all for attending. This is the, I think this is the final online applied PD talk this quarter. Today's speaker is Jennifer Mueller. Jennifer and I were colleagues for the 2 brief years I spent at Colorado State myself. Jennifer got her PhD from the University of Nebraska in 1997. And after a postdoc at RPI, she's been at Colorado State ever since. Where she's been doing great work, a lot of it, or all, I guess almost all of it, related to inverse problems. That's resulted in numerous papers, collaborations. More than one book, or just the one book?
What'd you say?
More than one book, or just one book?
Just one book.
Just one book. And so today she's going to tell us about direct reconstruction methods in EIT applied to functional pulmonary imaging. Thanks, Jennifer.
Okay, thank you, Bernard. This is fun. I'm excited to give my first online seminar. Just an overview. I'll give an introduction to EIT. I won't assume people are familiar with it. I'll give an introduction to the D-bar reconstruction algorithm. That's something I've worked on for most of my career, and I'll tell you what's new with it, including the use of a priori data in this algorithm. We have ongoing work with the Children's Hospital of Colorado, supported by the NIH. So I'm going to show some clinical results, and the statistical results I show are pretty hot off the press. They're a little bit preliminary, but when you work with clinicians, a very important step as an applied mathematician is to either do it yourself or collaborate with a biostatistician to present the results in the ways that the clinicians are used to seeing them. So we have a clinical trial, and those are some preliminary statistical results I'll show at the end. So what electrical impedance tomography is, it's a medical imaging technique in which low-frequency, low-amplitude current is applied on the electrodes. This is an image from the EIT lab of a picture of a young boy being imaged for pulmonary function. We have electrodes placed around the surface of his chest, and we apply current on these voltages. It's low amplitude, low frequency. You can't feel it at all. We measure the voltages on all the electrodes simultaneously, and we solve an inverse problem to determine the conductivity and the permittivity in this cross-section of his chest. So mathematically, if we denote the admittivity by gamma, the real part is the conductivity sigma, and the imaginary part is also called the susceptivity, which is I omega epsilon, where omega is the frequency of the alternating current that's being applied. So in our lab, it's 125 kilohertz, and epsilon is the permittivity. So that is a measure of the medium's ability to store a charge, whereas the conductivity is a measure of the medium's ability to conduct a charge. So this is really governed by Maxwell's equations, but in the human body, the magnetic permeability is very small. And the fact that we're applying time harmonic currents allows this to be simplified to the generalized Laplace equation. So the governing equation for the forward problem is divergence of gamma grad U equals 0, where U is the electric potential, also known as the voltage, in the interior of this domain. And then on the boundary, the voltage is denoted by F. That's the Dirichlet boundary condition. The current is the Neumann boundary condition, gamma outward normal derivative with respect to U on the boundary, so that's the current density. And the data is the Dirichlet to Neumann map, or equivalently the Neumann to Dirichlet map, in which you, well, the Neumann to Dirichlet map is the map in which you apply currents and measure the voltage, so that would be the inverse of the Dirichlet to Neumann map that I have here. It's interesting, in the EIT literature, all of the theory is posed in terms of the Dirichlet to Neumann map, whereas in practice we use the Neumann to Dirichlet map because the process of applying currents and measuring voltage is a damping operator, so noise is minimized, whereas if we were to apply voltage and measure current, noise would be amplified. In theory, there's no noise, and you don't have to worry about it, and that's why I guess traditionally it's the Dirichlet to Neumann map. So that means your data is the knowledge of any current density arising from any voltage that you would apply along the surface here. And ideally, you know it along the whole perimeter of your boundary. But in practice, your measurements are on electrodes. There's a finite number of them that you have finite precision, and there's noise. So although this is sufficient data to recover the conductivity or the admittivity. In practice, it's not because of these restrictions to a finite number of electrodes, finite precision, etc. And so this is a severely ill-posed problem. It's typically attributed to Calderón for the mathematical origins of this problem. So in a conference in Rio in 1980, he asked, can the admittivity be recovered from current to voltage measurements? And his interest arose from his time doing geophysical prospecting in Argentina. He wasn't really thinking of medical imaging. And he asked, if so, how could it be reconstructed? So he proposed a method for the linearized problem. It was a direct method. It used complex geometrical optic solutions of Laplace's equation to reconstruct the conductivity from the Fourier transform. And this paved the way for direct methods for solving the nonlinear EIT problem. So historically, both iterative and direct methods have been utilized, but mostly iterative methods were used until more recently. So some medical applications of EIT, here's kind of a laundry list. Location of epileptic foci, breast cancer detection, prostate cancer detection. Our group is quite interested in monitoring ventilation and perfusion in patients with acute respiratory distress syndrome. We're also interested in diagnosing atelectasis, pneumothorax, oh, I have a typo there, lung collapse, hyperdistension, and pleural effusion in real time. We also are engaged in this study with Children's Hospital of Colorado that I'm going to tell you about. Those are patients with cystic fibrosis, and so we're looking at the visualization and quantitative measures from pulmonary function tests. I'll talk more about those when we get to that part. Identifying regions of obstruction or consolidation in patients with lung disease, and again, that relates to our studies on the cystic fibrosis patients in Denver. Okay, so why EIT? There's a lot of medical imaging techniques out there, including MRI, CT, that provide, terrific spatial resolution and good diagnostic properties. Well, one thing is with EIT you have fast data acquisition and very good temporal resolution. That's not the case with MRI or CT, although there are things like functional MRI. The patient still has to lay in there for quite some period of time. Contrast agents are used for functional MRI. Whereas with EIT, it's very natural. We acquire data at 30 frames a second, and we can do it simultaneously, for example, with pulmonary function tests. Well, it's non-invasive and non-ionizing. So the fact that CT induces ionizing radiation in the patient is really a big deal. The FDA and the NIH both have initiatives for reducing ionizing radiation that's going to patients, and CF patients are particularly susceptible to ionizing radiation. There's studies that show that they are at a greater risk of developing cancer. And children, of course, limit the amount of ionizing radiation they receive in a lifetime. So a lot of these lung diseases require follow-up scans, for example, lung cancer, different kinds of pulmonary chronic diseases require follow-up CTs. And so it's not just one incident receiving a high degree of ionizing radiation, but it's repetitive. Okay, it's inexpensive in comparison with MRI or CT, and it's portable. And finally, regional information about ventilation and perfusion can be obtained in real time. So I thought I'd give you this little introduction to the EIT lab at CSU. We have a lab with EIT. Sorry, what?
Can I ask a question?
Yeah.
So there must be disadvantages. I mean, otherwise we would only use that and not the more expensive option. So what are the disadvantages?
So the most glaring disadvantage is the lack of spatial resolution. I guess I haven't put up any EIT images here yet, but you will see that they do not compete at all with the spatial resolution of CT scans or MRIs.
Okay, thank you.
Yeah, that's the big one. However, they do have their niche. Okay, so here's just a brief introduction to the lab. Some of these people have since graduated. This is about a year old. Michelle graduated in May. She's now a postdoc in Denver. She's from the School of Biomedical Engineering. Melody recently graduated. She's in Spokane, Washington at Gonzaga University. These two undergrads have also since moved on, and a few people have moved in to take their place, so I should update the picture. Okay, I'll just spend a few minutes showing you the hardware. So this is our system on a cart. This is the tank in the background for which we take data to validate our algorithms. And this is the EIT box, function generator, obviously the monitor. We have a medical isolation transformer for patient safety. This is the computer that contains the A to D boards. Current sources are in here, and a DC power supply down here. So what we do in data acquisition is apply current pairwise on up to 32 electrodes at a user-specified frequency, which is usually 125 kilohertz. The data acquisition is approximately 30 frames per second. We measure the real and quadrature component of the voltage signals on the electrodes, which in this picture are on the tank. And we have this modular and portable design so we can swap components out if we need to update or fix anything. ACE1 stands for active complex electrode. There's little chips next to each electrode that measure the current that's actually getting applied on each electrode. So if there's stray capacitance or loss along these cables, we have accurate measurement at the electrode of the actual current being applied. Okay, so now reconstruction algorithms. The reconstruction algorithms are generally classified into three categories. Least squares algorithms that measure the fit to a predicted estimate of your conductivity distribution in the interior to the measured data. So your data, again, are these voltage measurements. You can solve a forward problem with a guess at your conductivity distribution, compute the voltages from that forward problem, which you may solve with finite elements, for example, and then look at the difference in those voltages and try to minimize those, so you update your conductivity at each step. There's usually a penalty term because this is such an opposed problem, or it's also known as a regularization term, and there's many techniques, and that's an active area of research, is how to best regularize your least squares algorithm. Linearization algorithms, there's actually EIT methods using back projection, there's one-step least squares algorithms, and Calderón's method is another linearization algorithm. Statistical inversion usually uses Bayesian techniques. Its disadvantage is that it usually is slow to converge, but it doesn't require smoothness assumptions, and it's very nice for including a priori information. Layer stripping, I'm not sure why I always include that, because it's been proven to be unstable when there's noise in the data, but it is a direct method. And finally, D-bar methods. So these are a family of methods based on complex geometrical optics solutions. So they get their initiative in Calderón's method with the complex geometrical optics solutions he introduced, but you end up solving a D-bar equation to directly determine the conductivity from the data. So I'm going to go through the steps of one of the D-bar methods in detail here. So they capitalize on the relationship between the conductivity and these complex geometrical optics to a PDE related to the inverse conductivity problem. So I wrote this in general terms because there's more than one D-bar method, and depending on which one you pick, it's going to be CGO solutions to a different PDE. Okay, so the one I'll show in this talk is based on a 1996 proof by Adrian Nachman for the inverse conductivity problem. So it's the global uniqueness proof, and the steps are outlined here. Well, maybe I'll quick mention these advantages of D-bar methods before I start in on these steps. That'll take a bit of explanation. So they have the advantages that they're nonlinear. They're mesh independent. You'll see that as we go through the steps. And so they're trivially parallelizable. And in fact, there's more than one way to parallelize them, but the trivial way is with respect to each pixel for which you want to reconstruct your conductivity. So the data is the Dirichlet-Neumann map. We'll denote it by lambda sub sigma here. And the CGO solution is a CGO solution to the Schrodinger equation. I'll show that in the next slide. That's obtained from a change of variables from the generalized Laplace equation. So we will denote that CGO solution by psi. And it depends on two variables. Z is going to be our spatial variable. We'll identify a point in the plane with a complex number z. So if x and y are your coordinates in the plane representing a cross-section of your domain, then we'll let z be x plus iy. K is an auxiliary variable that gets introduced. We'll see that shortly. It's a complex number, and it can be thought of as a complex frequency, but it's non-physical. T of k is the scattering transform. It's also an intermediate non-physical function that can be thought of as a nonlinear Fourier transform of the variable q. And mu is another CGO solution. It's directly related to psi. I'll give you that formula in a minute, but it's very simply related to psi. We solve the d-bar equation for mu directly to obtain sigma. Okay, so I'm going to go through these steps briefly. If people have questions, let me know. I'll try not to go too quickly. We'll have them efficiently on one slide. So the first step is we have our data, and remember that's physically related to the generalized Laplace equation. But this change of variables, Laplacian square root of sigma divided by the square root of sigma, and psi equal to the square root of sigma times u, allows us to change the generalized Laplace equation to the Schrodinger equation. Now, we studied the Schrodinger equation in all of R2 rather than just our domain of interest omega, because if we take sigma to be constant on the boundary, which is usually physically pretty realistic, but you can also use analytic continuation and just extend your domain a little bit to satisfy that. So then if sigma is constant, through this change of variables, q is 0, and so then we can just extend to all of R2.
Question?
Okay. Yeah.
So is this, the change of variables, that's basically generalization of what you have in one dimension to get any second order non-autonomous problem in Hill's equation form?
Yeah. Mm-hmm.
Okay. Nice. Cool. I didn't know that.
So now, in the Schrodinger equation, we've introduced the variable k. I didn't spell it out here, but k is that complex parameter that I mentioned. And so we require that psi has the asymptotic behavior e to the I k z, where, like I said, z is complex. It's our spatial variable. And k is the complex frequency. And so this is complex multiplication here. And so you'll see e to the I k z, since we have three complex numbers being multiplied together, will grow exponentially in some directions and decay in others. So e to the I k z itself is a CGO solution, and it's a CGO solution of Laplace's equation. So we require psi to be asymptotic to e to the I k z, and Fadeev, in the context of quantum physics in 1966, showed that there's a Green's function for that problem, the Schrodinger equation with those specific asymptotics, and we can call it little g sub k, the Fadeev Green's function. Well, capital G sub k is a fundamental solution for the Laplacian, minus the Laplacian, and then G sub k is a fundamental solution for this d-bar equation. So here, using the relationship between psi and mu, defining mu to be e to the minus I k z psi, knowing that the asymptotics of psi are e to the I k z, we know that the asymptotics of mu are 1. So it's asymptotic to 1 for large k and large z. And then a fundamental solution for the PDE that mu satisfies, which is this one right here, minus Laplacian mu minus 4ik d bar mu plus q mu equal to 0, has this g sub k as its Green's function. So the Green's function, little g sub k, incidentally, is related to the Green's function for just the Laplacian by a multiplicative factor of e to the I k z. So we can call them both the Fadeev Green's function. So the important thing here is that mu satisfies this Lippmann-Schwinger equation. So we have convolution with q mu and gk, and then its asymptotic behavior here of 1. Okay, so that took a while to get our CGO solutions built up, but now we really have two of them that are related very simply to each other through this formula. So with this knowledge, though, we haven't tied anything into the measured data. You know, we said we can go from this step to this step through this change of variables, but that all requires knowledge of sigma, which is what we want to reconstruct. So these equations that I'm giving you are all from Nachman's 1996 proof, and he established this equation for psi on the boundary. So psi on the boundary is given by its asymptotic behavior, e to the I k z, minus the convolution of the Fadeev Green's function with this difference in our Dirichlet and Neumann maps applied to psi. And this also comes from the Lippmann equation for psi. One can show that using Alessandrini's identity. So the only new notation here is that this lambda sub 1 indicates the Dirichlet and Neumann map if you had a constant conductivity of 1 in your domain. Okay, ran out of space. So now let's get rid of those and look at T of K. T of K is called the scattering transform. It's a nonlinear Fourier transform of Q, and it's given by, in its definition, e to the I k conjugate z conjugate q psi. So if we put in the asymptotic behavior of psi there, we would have the Fourier transform of Q evaluated at minus 2k1, k2, and that's why it can be seen as a nonlinear Fourier transform. But again, in this process, we need a relationship between T of K and our measured data, since both sigma and Q are unknown. So that's given by this integral equation on the boundary, e to the I k bar z bar. Again, this difference in Dirichlet and Neumann maps applied to our CGO solution psi. Okay, we've almost gotten there. Now one can show by differentiating the Lippmann-Schwinger equation for mu with respect to k conjugate that mu satisfies this d-bar equation. So the partial of mu with respect to k conjugate is equal to the scattering transform divided by 4 k bar times this exponential factor, which is modulus 1, times the conjugate of mu at zk. So that's the d-bar equation, or you can use the generalized Cauchy integral formula to write it in integral form as follows. You can also see this as convolution with the Green's function for the d-bar operator. Okay, so lastly, one recovers sigma from evaluation of mu at k equals 0 and squaring it. That can be seen in a straightforward way from the Schrodinger equation. I don't think I put it on here, though. No, I didn't. But if you go back to the Schrodinger equation, if you put in k equals 0, mu and psi are the same. If you put in this change of variables for q, you can see that you have minus Laplacian of mu plus the Laplacian of the square root of sigma over the square root of sigma equal to 0. And so mu must be equal to the square root of sigma when k equals 0. So that's the formal way of seeing it. Okay, I'm going to give you the steps one more time since I think that was a lot. So I have step 1 as approximating sigma on the boundary. In case the requirement that it be constant on the boundary is not satisfied, then you can approximate it and do the extension. Next, compute the CGO solution on the boundary from the measured data. This S is just the operator of convolution with the Fedaya-Green's function on the boundary. Next, one computes the scattering transform T of K from the measured data via this formula. I see that I use the notation lambda sub Q. When sigma is constant on the boundary, lambda sub Q and lambda sub sigma are the same, and the same goes for this. So this notation is the Dirichlet and Neumann map for the Schrodinger equation. You can totally replace it by lambda sub sigma and lambda sub 1 as I have before. Okay, this is the equation I just showed you, the integral form of the d-bar equation. One needs to solve that for mu and evaluate at 0, and then reconstruct by squaring mu to get sigma at the point z. So these are the steps in the direct algorithm. It involves solving a little series of integral equations and then just evaluation at the point k equals 0. So just to tie back to a couple things I said about it, the mesh independent piece is that notice no matter what mesh you choose to evaluate or approximate your sigma on, this ends up getting solved at each point z independently. So you don't have this relationship like you do in least squares methods between posedness and mesh size. You just evaluate at each z you want to. Which doesn't mean you can get infinite resolution here, it just means that it's independent of mesh. An approximation we often use that I just wanted to mention to speed things up is you can take a shortcut here. We found it works very well to approximate psi by its asymptotic behavior. One can show bounds on the accuracy of this. When you have a small contrast, this is a good approximation. And then the scattering transform can be approximated by replacing the CGO solution psi in that equation by the exp approximation. In other words, it's asymptotic behavior. And then continuing the method as before. I have to check my watch. Okay. So, nonlinear regularization. So a family of continuous mappings parameterized by a regularization parameter alpha is called a regularization strategy. If, as alpha goes to 0, when we take those mappings and apply it to our data, the difference between that and the actual solution, and I suggestively used the notation of our problem here, an L infinity norm goes to 0 as alpha goes to 0 for each fixed sigma in a permissible set Z. Okay, furthermore, these are definitions from Kirsch's book on inverse problems, by the way. A regularization strategy with this choice alpha of regularization parameter as a function of noise level epsilon is called admissible if the regularization parameter will go to 0 as the noise level goes to 0. And again, any fixed solution sigma, we have that the supremum over all of these noisy maps with noise level epsilon, that's the data, of our regularized solution applied to that data minus sigma, the L infinity norm goes to 0 as epsilon goes to 0. And this is just a bound on the noise in the data here. So what I'd like to show briefly from an article in the Science Journal of Applied Math together with Kim Knudsen, Avi Lassis, and Salmi Siltaman is that there's a way that you can regularize these direct methods by truncating the complex frequency K. And that constitutes a nonlinear regularization strategy. It's work from 2009, but I'd like to show that formulation briefly here. So the way that works is if you start from this boundary integral equation for psi, or CGO solution on the boundary, and you have noise in the data with this bound and this appropriate choice of Sobolev spaces, then the way to regularize is simply to truncate your domain in the K-plane. So this is the characteristic function, and all this notation is saying is that we're going to solve that boundary integral equation for truncated values of K, so K in a disk of radius R. And then we'll use those CGO solutions in our equation for the scattering transform, and so we'll only solve in a disk of radius R in the K-plane. And we'll denote those by psi VIER and T VIER. Their boundary integral equation and R indicating our radius of truncation. Okay, so the regularization parameter alpha in the nonlinear regularization strategy is just 1 over this truncation radius, and it depends on the noise in this way. And then the mapping gamma, capital gamma, in the definition is just defined to be, well, it applies to the data, our noisy Dirichlet and Neumann map, and we go through the steps of the D-bar algorithm, arrive at mu using the truncated data, truncated CGO solution is a better way of saying it, get the mu we get from the method by using that CGO solution in there, evaluate at 0 and square it. Okay, so this is well defined for small alpha, and it's an admissible regularization strategy. It satisfies the requirement that this goes to 0 as alpha gets small, and there's this bound with respect to the noise level. Or another way of saying that is you can use that to choose your truncation radius. If D is half the diameter of your domain, then the truncation radius, in theory, should be negative T times log epsilon. We need the negative in there since we're assuming epsilon's less than 1, with this bound on T. So then, with our mapping now, with the output being denoted by sigma R VIE, that's the output of the gamma, if we have sigma sufficiently smooth as the noise level goes to 0, our reconstructed sigma will approach the actual sigma in L infinity norm. Okay, so like I said, that's work from 2009, but I like to mention it since it gives a strong theoretical underpinning to the practical D-bar method that we use in our lab and in clinical data. So what's new? Since that time, the D-bar reconstruction method has been applied to both conductivity and permittivity, so also known as complex conductivities. Students involved in that include Alan von Herman, Sarah Hamilton, and Natalia Herrera. my student Melody Dodd did a real-time implementation of this method for her thesis. And she also worked on the use of priors. So I'd like to spend a couple minutes on the use of priors. So priors are used very widely in reconstruction algorithms that are based on least squares. It's very natural to add a penalty term, and it's a natural place to put information you know about your solution. For example, you know that there's 2 lungs and a heart. This is in the tank in the lab. You can put it in your penalty term. It's not so clear how to do it in the D-bar method, so that's what I'd like to show you briefly and the effect that it has. So in this quick figure, what you see is a regularization method that used the spatial information of the heart and lungs, perturbed a little bit, and taken from this photo. No information about this inhomogeneity in here, which is a copper pipe, and yet it sharpened the image in this way. In this slide, I don't have the original reconstruction, but in the original reconstruction, it's more blurred than it is here. And yet, even without the a priori information about the copper pipe, it shows up nice and clear, pretty clear. It should be bright red because it's copper, so it's still masked somewhat. Okay, so very briefly, I'd like to explain that. So if you have a conductivity distribution sigma, you can approximate the prior with polygonal approximations to the organ boundaries, for example, from a CT scan. What I'll show you here will be from simulated data, however. So you can use this polygonal approximation to the heart, lung, aorta, and spine. And then we need to mollify it because remember, to compute Q, you have to take a second derivative. So mollify it, compute Q, and then you can obtain a prior for your conductivity distribution, which will denote sigma sub PR. Okay, so the whole idea is to include that information in the scattering transform. So instead of just taking the scattering transform from the data on a truncated domain, we'll add in a little bit wider annulus in which we put the prior, and then piece that together, and then still truncate outside of some radius R2. And then one can control the influence of this prior by adjusting this radius R2. If you take R2 to equal R1, there's no prior, and the larger you let it be, the more influence the prior will have. Okay, so to compute the prior, we just use the definition. Because for the prior conductivity, we know what it looks like. We can compute the potential that goes along with it and use the definition of the scattering transform. Then one can numerically solve the Lippmann-Schwinger equation and get a CGO solution corresponding to that, which we'll denote by mu prior. Now, mu prior I've introduced because there's a second piece where one can introduce some prior information besides just the scattering transform, and that is in the d-bar integral equation. So, in fact, this asymptotic behavior of 1 that we used to have here is only accurate if you're going all the way out to infinity with your r's. In practice, we're not. So we can introduce this weight, alpha, and for alpha equal to 1, there would be no prior mu int included in that term. But for alpha equals 0, there would be a strong weight, and then you can take alphas in between. And what it is I won't go into the derivation of that one, but from, if you look at the Green's function approach to obtaining that integral equation, one takes a larger and larger disk of radius r and moves out until you get the asymptotic behavior of 1. But before that, you get values of mu in the disk. So very briefly, that's where that comes from. And so one can replace that by mu prior. So as
another question.
Go ahead.
Do you ever have to worry about the presence of discrete spectrum of eigenvalues as opposed to continuous spectrum?
No, you don't. There's no, so there, in this particular method, if you go back to Nachman's global uniqueness proof, he showed that there's no exceptional points for conductivities, for conductivities, period. So the Schrodinger equation doesn't have any exceptional points for this type of potential that arises from conductivities. They're called conductivity type potentials.
So what makes them special that they don't have any bound states?
Gosh. Oh, how to
Well, I guess if they always have the wrong sign, if they're always positive, then you would.
Yeah, they are always positive. That's true. It's a little more technical than that. You have to look at the bounds on the scattering transform as well. At least that's how Nachman does it in his paper. But it's true, they are always positive since they're conductivities.
Okay.
Good enough?
Yeah, but also a question on the previous slide. You say we numerically solve the Lippmann-Schwinger equation. How is that done?
We use a multi-grid method. So, well, it's just two grids, a fine and a coarse method, and you don't even have to use the grids. But the key to it is here you have this convolution. So if you take FFTs, you can change this convolution, to a product. So we use FFTs on this piece, just to do it really briefly, and then IFFTs to go back. So you just hit this thing with the FFT and the IFFT, compute in the Fourier domain, the product, and then IFFT back on a grid. Yeah, carefully chosen grids. So we do two grids, a fine grid and a coarse grid, but that isn't necessary for convergence of the method. It just speeds it up.
Okay, thank you.
Okay, so just to conclude the bit about the a priori algorithm, in fact, using this kind of a priori method also consists of a nonlinear regularization strategy. So I know the notation's getting a bit cumbersome, but if you fix, so we have two regularization parameters going here. Let's say you fix the one called alpha, and you have noise level epsilon. Then we could denote that mapping, that solution method, by capital gamma sub beta of epsilon. And when you apply that to noisy data, go through the process I just described, you get your mu, evaluate at 0 and square it to get your approximation sigma. And then here beta is 1 over the interior regularization parameter, or cutoff frequency 1 over, so it's 1 over R1. So with that, Melody and I showed in an article that just appeared this year in the Science Journal of Imaging Science that this is a well-defined reconstruction algorithm, and it's a nonlinear regularization strategy with this kind of a bound again on the difference between the computed noisy data conductivity and the actual conductivity. Okay, and then
yeah. An exponent of 1 over 14.
Oh, it's a mess. It's kind of technical how you get the 1 over 14.
Okay.
You can read the proof.
I don't think I've ever seen an exponent of 1 over 14 in a...
Well, the original version also had the 1 over 14. And so you can trace it all the way back to the... Yeah. We laughed about it. So just to quick show you how it works. Oh, I thought, just a second, there's a slide missing, actually. I want to see if it's out of order. No, I don't know where it went. That's strange, but it's okay. So the slide that's missing shows you the actual conductivity distribution, but it's all right because it's drawn in anyway. So you can see the boundaries. It's the slide I showed you before, really, this one. And so using the prior in this method, there's no inhomogeneities here, no pipe in the lung. In this case, I'm going to show you. This one I just chose from our paper to illustrate the influence of the prior. So going this way, we're letting R2 be fixed and alpha be decreased. So decreasing alpha increases the influence of the prior. And then going down, we let alpha be fixed and R2 increase, which also increases the influence of the prior. And so here's the reconstruction of the conductivity with no prior. Here's with the strongest prior we considered, alpha equals 0 and R2 equals 10. And so you can see features like the spine that were pretty blurred out in the original image show up quite clearly in the version that uses the prior. The lung boundaries sharpen up and the presence of the aorta sharpen up. Of course, it's what you'd expect. If you add information that's known, the conductivity distribution should improve. And so things get more interesting on, for example, experimental data where you have priors where you don't assume that there's a pathology, like I showed you with the copper pipe in the tank. Okay, I want to make sure I have a little bit of time to talk about clinical results. So we're looking at patients with cystic fibrosis in collaboration with doctors at Children's Hospital. Patients with cystic fibrosis have a whole suite of health problems. It's a genetic disease characterized, as you can see, by lung congestion and infection and malabsorption of nutrients by the pancreas. In fact, the body can't properly process salt. And so this lack of ability to metabolize the salt causes the mucus to be sticky instead of slippery, and results in all kinds of problems. In particular, we're going to look at the ones that cause lung disease. So this sticky mucus results in air trapping and consolidation due to mucus plugging and airway thickening, which makes them very susceptible to bacterial infections, and sometimes they get blood in the mucus. So sometimes whole regions or lobes of the lung become air trapped, meaning that air isn't flowing in and out, it stays in there. Okay, here's a few statistics in case you haven't heard much about CF. There's about 30,000 people living with CF, 70,000 worldwide. About 1,000 new cases are diagnosed yearly. It's genetic, so if both parents have to have it, and if they do, a person has a 1 in 4 chance of getting it. More than 75% of the cases are diagnosed by age 2, and this is a good thing. Nearly half the CF population is above age 18 now. It used to be that in the very olden days that children wouldn't live past age 1, and the lifespan has been steadily increasing, especially due to the CF Foundation. So EIT data can be collected at the same time as the pulmonary function tests that these patients do. If any of you have asthma, you've probably done a pulmonary function test. What you do is you breathe into this mouthpiece that seals over your lips and your nose is sealed. You take a big breath in and you exhale as hard as you can, all the air out as fast as you can and as much as you can. So here's a healthy volunteer at the hospital doing that. And here's a sequence of conductivity images collected during that patient's subjects, that's not a patient, PFT. So what you see in these images are red for the heart because it's a region of high conductivity, blue for the lungs. Air is very resistive or not very conductive, and so it's showing up as blue. Now, in these pictures, there was a reference image, and the reference image wasn't quite at full expiration, so when the person reaches full expiration, the lungs have actually become red because they're more conductive than the reference image. And then these are some recovery breaths. So here you can get an idea of what the images look like in a healthy volunteer. We form different kinds of outputs, and the spirometer is the machine that they're using. There's all kinds of automatic outputs that the doctors use for diagnostics from the spirometer, such as measuring the volume of air in the lungs at maximum inspiration, how much volume they can exhale after 1 second, how much volume they've exhaled when they really reach the end. They can't exhale anymore. And this ratio called FEV 1% FVC, which is their total lung capacity minus the volume exhaled in 1 second, divided by the total lung capacity minus the total volume of air exhaled at the end of forced expiration. And this isn't 0, there's always a little bit left over, times 100%. So we identify key time points in our data sets from a PCA of the reconstructed images. So here's a typical PCA from one of our subjects. So from this, we can see the maximum inspiration when the inhalation started before the big breath in. Here's the big exhale, 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 exhale. There's 1 second. We know our frame rate of our data collection. And so from that, we can calculate which frame corresponds to 1 second after their maximum inspiration. Here's the maximum expiration, and then these are just one recovery breath in this picture. Am I supposed to end 5 minutes from now, or how much time do I have, just so I kind of know?
Well, as you all know, seminar speakers kind of make their own rules. So yeah, it's advertised as a 50-minute talk. So if you could end by say 55, that'd be great.
Okay, perfect. Okay. So from our EIT images, we can calculate a regional estimate of FEV1% FVC based on relations in the conductivity distribution. So although we don't have volumes, we can calculate volumes or derived approximations of volumes from the conductivities times the pixel sizes. Here, the pixel sizes aren't included because they divide out in this ratio. But since conductivity is directly related to the amount of air in the lungs, we can get an estimate of FEV1% FVC from our EIT images, and we can get something that the spirometer can't get, and that is a pixel-wise measure or regional measure. So here's the formula for that. I've used pretty much the same notation. This should have been an FVC, really. We use it. We use EFE with the clinicians for end forced expiration. That's what that was, and 1 second instead of FEV1 right here. But same formula. And then one can also get a global value to compare to the spirometer output by summing over all the pixels. Okay, so we did this for various groups in our study. Group 1 consists of healthy control subjects, ages 2 to 21. Group 2 were CF patients, ages 2 to 21, who were receiving a CT scan as part of their standard of care. And then group 3 are CF patients between the ages of 8 to 21. And we chose those ages because subjects or patients over age 8 do spirometry. Younger ones don't. They don't have the skill to cooperate well with that. And these patients were hospitalized for pulmonary exacerbation, which is things like a lung infection. So we imaged them on admission and again at discharge. So we collected data during tidal breathing, breath holding, and PFTs, looking for regions of air trapping and consolidation, developing an algorithm for calculating the FEV1% FVC, and doing a statistical analysis of the results. Here's another reconstruction of ventilation in a patient. This one, you can see the time dependence. It's a movie. I think this one is just ventilation, not during PFT. Yeah. Now it's a PFT for exhaling, 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 exhaling. I forgot that I have the PFT there. So that's the long exhale. Now they're breathing in again. Breathing out. Breathing in. Okay. So we segment those images and obtain our derived measures. Ooh, I didn't want to advance for me. Let's see. Yeah, okay. So 2 case studies. This subject, G2014, was a 10-year-old male who was hospitalized and received a CT scan. The radiation report showed that he had extensive regions of air trapping, which was approximately 50% of both lungs. These are his CT scans. This is just diaphragm here. There's a lot going on in his lungs, unfortunately. And the shading indicates regions of air trapping. I think you can maybe see here this darker, it's subtle, but this darker blackish region, grayish region here is air trapping. This is some air trapping, but not as extensive as here. On the right is what we have formed called a secondary difference image, and we may be seeing some regions of air trapping. There's this here. We aren't picking up changes in this upper lobe of the lung, probably due to all of this consolidation. But this air trapping, we are hypothesizing, is indicated by this bright region. And due to time, I'm not going to dwell on how the secondary images were computed. Another subject, just to give you an idea of what we're doing, is this subject G2012, a 17-year-old female who's also hospitalized. This lung looks totally air trapped. This one seems to have some air trapping here. This is called linear consolidation, but you know, Bernard, you were asking what's the disadvantages. Here's a disadvantage. We're not going to see any linear consolidation on our EIT images. The resolution simply isn't good enough. Okay, so this is the EIT image of their lungs at full inspiration, and here's the segmentation we computed. And I just want to mention that while the CT scan is ground truth, it's not exactly the same plane as our images. And this is the expiratory image, and these were both inspiration. So it's better to compare to this one. Okay, the movie's not going to play, but that's okay. You've seen one movie, so I'm going to skip over that. Oops. And show some statistical results. So one thing we've been interested in knowing is, can we discriminate between the different groups using this measure of FEV 1% FVC derived from the EIT? That's one way of validating this as a measure before going to town with the regional information you could derive from it. So we wanted to see how well one could discriminate between control, group 2, remember they have CF, group 3, they were the ones initially hospitalized, group 3 post is when they are discharged. And we had several measures here. This one you can disregard. I also gave a talk similar to this recently at RPI. And I included this one since it was also hot off the press then, but we have since abandoned, we've since abandoned this medium measure. This one's good. So the kind of statistical analysis you want to do is to look and see how well it discriminates, and the p-value indicates whether it's statistically significant or not, and of course that's also a function of your sample size. But interestingly, the EIT measure discriminated between groups, meaning this one here, with a p-value of 0.07, so that's right on the border of statistical significance, whereas the spirometry p-value is 0.21, which actually is poorer than the 0.07, isn't generally considered statistically significant. So we were encouraged by that. Regression analysis showed a strong correlation between our measures and spirometry. And then another method or another measure one can look at is just looking at the pre and post patients. So I have 7 of them here. G3005 had an electrode issue, so that one's not included. And what you see here is their FEV 1% FVC scores averaged, because each visit they do multiple spirometry tests. So we took anywhere from 3 to 12 data sets of them doing spirometry, depending on what was clinically indicated for them, pre and post. So those were averaged. And what one would expect to see is that they should get better, right? So they should do better on their FEV 1% FVCs from pre to post. So these lines should either be, let's see, we have pre to post. So these lines should either be increasing or they might be fairly flat. And the 2 measures to pay attention to are the green and the blue. The PCA is less effectively found for this one. So in every case, we have that the EIT measure, which is denoted by the pitch top here, is either flat or increasing. In some cases, the actual is quite flat. In a couple cases, the actual goes down, which is interesting because we would expect them to be improving, and so their spirometry results should improve. So at the moment, this is just an interesting finding that in every case, the green EIT measure shows improvement from pre to post, whereas in 2 of the cases, the actual did not. So that's a sort of a sampling of the statistical results we're getting. There's more, but I'm just going to show you those for today. So I want to thank you for your attention. And if you'd like to learn more about EIT or linear or nonlinear methods, I'll put a quick advertisement up for the book.
Hey, thank you. More questions?
I have a question. Hi, Jennifer.
Hi, I'm going to try to make it so I can see you now. Okay.
Okay. So I have a question about like how fast is this reconstruction program is? Like for a fixed pixel, how much time does it take?
Per pixel?
Yeah, so, like you can. I know that you can do them parallelly, so it may take more time to generate a whole picture with multiple pixels, but you can do them like distribute the job to different cores. So just one pixel, how much time does it take?
So you can distribute it based on pixels, Or when you're making movies like this, you can distribute it by frame also.
Okay.
And we found that by frame is actually faster than by pixel because of the setup time for certain functions. So the rate, I can tell you the time. It's harder to say per pixel, and per pixel would be tiny. So to do one frame is I think we had, it depends, but we had 0.0625 seconds, I think. So 0.065 seconds per frame.
Okay.
Real time, if you're going at, I think it's 24 frames a second. But I'm not sure if it's 24 or 30. I'd have to calculate that again. So the real-time paper appeared in the journal called Inverse Problems in Imaging. I think it's in 2014. And everything's really spelled out there, like how many frames a second, what kind of computer we timed it on. We timed it on a couple different ones, and we used various numbers of cores. So it tells about how many cores, and then of course it depends on how many pixels you're using, if you use a fine mesh or a coarse mesh, because even though it's mesh dependent, you still have to do that in your pixels. So if you want all the gory details, you should go to the Inverse Problems in Imaging paper.
Like, I know, like, is there any error control, like how many, like, points I need to use to, like, solve the inverse problem?
How many wets? I'm sorry.
Like how many mesh points I need to solve for the inverse problem, not the mesh for the pixels, but the mesh for the, like, the integral equations and, like, for
the K-grid? Yeah, we often use 2 to the 7th.
2 to the 7th. Okay.
Yeah. 2 to the 6, 2 to the 7th.
Is that kind of depending on, like, where the pixel is? Like, is that parameter dependent?
Which parameter? Sorry.
Like, when you reconstruct the image for each pixels, does the position of the pixel affect the number of points you need to use to get the same accuracy?
Not really. You yes and no, because if you're in a very flat blah area, I think you could get away with a coarser K-grid. But it's more efficient just to choose one K-grid and go with it.
Mm-hmm.
So 64 points in a K-grid is kind of a good rule of thumb. But then when I say that, then it depends on your truncation radius and things like that. We have a lot of empirical experience with how far out you have to go in K. When you have experimental data, when you have simulated data, you can go much farther out with K because you don't have noise, or you can control the noise level. So, numbers that I tell you are going to depend on a lot of things. But we always report them in the paper, so you can, in all of our papers. So if you want to check our grids, you always can.
Okay, thank you.
Sure.
More questions? Well, if there's no more questions, let's thank Jennifer again. Thank you very much. Please pass on my greetings to whoever is still there after all these years.
Okay.
And hopefully it won't be another 6 years.
Yeah, okay.
All right.
Sounds great. Thank you. Thanks for inviting me.
Thank you.